Good morning, my dear students. So now I'm going to tell you about the third case, that is a third damping system case. Okay, that is called as a critical damp system. Okay, so this question is also very important for the point of examination. Okay, so normally we know that the damping is nothing but what? It is the resistance of a body to the motion of a vibrating body is called as damping. Okay, again based on the damping condition, we are going to classify it into three types. Okay, if damped system is normally denoted by zeta. Okay, that symbol are already seen in the last class. Okay, so normally damped is nothing but if the damping factor is greater than 1 means we are going to call as overdamp system. If it is less than equal 1 means we are going to call as underdamped system. And it is now the third case is critical damp system equation. Okay, if the damping value is equal to 1 while solving the problem, we are going to say that that particular system is called as a critical damp system. Okay, so let me derive the equation of this critical damp equation. Okay, so this is also very important question for the point of examination. Okay, so they may ask you question like this: explain the response of a critical damp system, or they may ask you derive the critical damp response equation. Okay, so here the condition I given here, critical nothing but critical damp system means you will understand that if the zeta value is equal to 1, then such particular systems are called as a damped critically system. Okay, so any spring mass damper system. Okay, if you solve that value, so damping factor you are going to get, if final answer is 1 means the whole system is called as a critical damp system. Okay, while solving the problem we are going to understand this. Okay, so otherwise if here I shown here the different types of conditions. Okay, so these conditions they may ask you in the competitive examination. Okay, so zeta is equal to 1, we are going to call as a critical damp, or C is equal to Cc. Okay, C is nothing but damp and Cc is nothing but critical damped. Okay, if that C is equal to Cc, then again we are going to call as critical damp system. Okay, or C by 2m is equal to square root of the natural frequency, that is K by m, is also called as a critical damp system. Okay, or C square is equal to 4mk, so that particular system is also called as a critical damp system. Okay, so here let me understand the definition. Okay, so here when the damping factor is equal to 1, such systems are called as a critical damp system. Okay, so critical damp occur normally when the frequency of the damped vibration is 0. Okay, the during such conditions we are going to get this critical damp system. Okay, the entire that spring mass damper system frequency normally is equal to 0, then such type we are going to get what, this critical damp system equation. Okay, when the roots are equal, and here in this critical damps the roots are equal and the real. Okay, so such systems are also called as a critical damp system. Okay, so this type of the damping is avoided because the mass of the masses, okay, moves back rapidly to its equilibrium position. Okay, so normally the as compared to overdamp system and underdamp system, so this type of damping we are going to avoid in almost all the system. Okay, because here the movement of the particular system is very fast. Okay, from its mean equilibrium position. Okay, so in this system the roots are real and equal, and for the critical damp system is equal to 1. Okay, so this line you have to make it by heart or whatever you want, just you remember this. Okay, so in the critical damp system the roots are real and equal. Okay, and zeta value is equal to 1. These 3 points are very important in critical damp particular system. Okay, therefore we know that the roots for this particular is s1 is equal to minus zeta plus square root of zeta square minus 1 into omega n. Okay, so here the zeta value is equal to 1, just to substitute in that equation you are going to get what, minus omega n. Okay, so similarly second root, that is s2 is equal to minus zeta minus square root of zeta square minus 1 into omega n. Okay, so just to substitute you are going to get minus omega n. Okay, so these are the roots plus or minus. Okay, so therefore the s1 and s2 is equal to minus omega n. So I hope you understand up to this. Okay, now we are going to go further steps. Okay, because of the repeated roots, okay, we are going to in the both the cases in the above cases, that is omega minus omega n minus omega n, both s1 and s2. Okay, therefore the approximate solution is we are going to get what, x is equal to c1 of e to the power of s1 t plus c2 C2 into T e to the power of S2 into T. This is the approximate solution we are going to consider while solving the critical damped system equation. Okay, therefore you just to substitute where S1 and S2. Okay, S1 is equal to minus omega n, S2 is equal to also omega n. Okay, so x is equal to, here just to substitute C1 is equal to e to the power of minus omega n t plus C2 t e to the power of minus omega n into T. Okay, just here after substituting this value, here we are going to get what, common is equal to e to the power of minus omega n t is a common. Okay, just to take the common inside what c1 plus c2 t into, that is the whole bracket is equal to e to the power of minus omega n into t. Okay, just to take the common e to the power of minus omega n into t, so whatever you are going to get inside, you write it, that is inside is c1 plus c2 into t. Give equation number 1. Okay, so here for up to this you have to remember that the approximate solution for the critical damped system is x is equal to c1 e to the power of s1 t plus c2 t e to the power of s2 into t. Okay, so we are going to substituting, we are going to get equation number 1. Okay, so where normally the c1 and c2 are constant and the value determined by the putting the boundary condition. Okay, normally we are going to calculate the c1 and c2 value by applying the boundary condition. Okay, where c1 and c2 are called as constant. Okay, so let us assume the mass of a the mass has been displaced at a distance of x naught. Okay, so normally the spring mass damper system just to displace at a distance of x naught from its mean equilibrium position, and it will release with an initial velocity of v naught. Okay, then the boundary conditions are just to disturb the spring mass damper system with an that is the displacement of x naught and with an velocity of v naught, so that we are going to get the boundary condition. Okay, that boundary conditions are this. Okay, x is equal to x naught at the time t is equal to 0. Okay, give equation number 2. Okay, similarly the velocity x dot is that is the displacement velocity. Okay, v naught is equal at a distance of t is equal to 0. Give equation number 3. Okay, so in the damping particular system, x is indicate that the normal x is indicate that displacement. If you differentiate that you are going to get what? Velocity. Again, if you differentiate means you are going to get acceleration. Okay, x means displacement, x single dot is called as velocity and x double dot is called as acceleration. Okay, so now the boundary condition we know that, so we have got that. Okay, now differentiate equation with respect, we differentiate equation number 1 with respect to x. Okay, with respect to t. So what we are going to get, just equation differentiate, we are going to get, this is, see here, the differentiation of this e to the power of minus omega n. Okay, so this, okay, just c1 plus, just to differentiate that equation, dx by dt is equal to x naught. Okay, if you differentiate c1 as it is and differentiation of that, okay, c1 minus omega n into e to the power of minus omega n into t. So here just to c1 e to the power of normal e to the power of x is e to the power of minus x, that you are going to write here. Okay, c1 minus omega n e to the power of minus omega n into t, plus similarly c2 is equal to t, that is a what? Constant term, minus omega n whole to, that is into e to the power of minus omega n t, plus c2 is equal to e to the power of minus omega n t. Okay, so just to differentiate that you are going to get, okay, that is a product formula here. Okay, so there again you resimplify that x1 x dot is equal to minus omega n c1 e to the power of minus omega n into t plus c2 e to the power of minus omega n into t minus of omega n into t c2 e to the power of minus omega n into t. Just to rearrange the what you got the differentiation of the above equation. Okay, again further you resimplify here. Okay, here also c1 and c2 are let us common. Okay, so x dot is equal to c2 e to the power of minus omega n t minus of omega n, okay, e to the power of minus omega n into t. So inside is c1 plus c2 into t. Okay, give equation number 4. Okay, so what we did up to here, just to approximate take the approximate solution. Okay, so just substitute, you are going to get one final equation. Give equation number 1. Okay, just to disturb the whole spring mass damper system within velocity and displacement section v naught, so that we are going to get boundary condition. Okay, so assume boundary condition, give equation number 2 and 3. Okay, again from the equation number 1 you differentiate with respect to t, you resimplify, you are going to get equation number 4. Okay, now the put equation number 2 in equation number 1. Okay, so we know that the equation number 2, that is x is equal to x naught at time t is equal to 0. So if you put substitute in the equation number 1, what we are going to get, x naught is equal to c1 value. Okay, so we got the c1 value. Okay, so again similarly you find c2 value, that is put equation number 3 in equation number 4, we are going to get what, v naught is equal to c2 minus omega n into c1. Okay, for this from this c2 is equal to v naught plus omega n into c1. Okay, therefore we got the c2 value. C2 is equal to what, v naught plus omega n into x naught. Okay, give question number 6. The main aim of by doing this simplification is we are going to get what, c1 and c2 value. Okay, after getting the c1 and c2 value, just to substitute in the equation number 1, that is put equation number 5 and 6 in equation number 1, so that therefore we got what, x is equal to x naught plus v naught plus v omega n x naught into t. Okay, whole square bracket into e to the power of minus omega n into t. So this is about what the equation number 7. Okay, what we got this, so equation number 7. Okay, again divide and multiply both the, that is a divide and multiply with omega n, that is a natural frequency, we are going to get what, x naught plus omega n into v naught divided by omega n plus omega n square, because this we are going to divide and multiply, okay, omega n into x naught into t, square root of the whole bracket is equal to e to the power of minus omega n into t. So there omega n going to get cancelled, so remaining you write down here x is equal to x naught plus omega n v naught divided by, that is vn, plus omega n x naught, okay, whole to the power of, that is a bracket t whole to the square bracket into the e to the power of minus omega n into t. Okay, so again you will simplify that, you are going to get this x is equal to x naught plus omega n into t v naught divided by omega n plus x naught, okay, into whole bracket e to the power of minus omega n into t. So this is about the equation 1. What we are going to get, from the critical damp particular system, this is an equation number 8. Okay, this equation number 8 is called as a critical damp system, that is the response of critical damp system. Okay, so let me understand from the graph also. From the graph, the value of x, okay, let us assume the value of x is going to decreases with as increasing time. Okay, with as time is increases, we are going to get x is a decreases, okay, and tends to 0. Normally it is going to reaches to the 0 as the value of x decreases as t increases, okay, and tends to 0. So you just to observe the diagram here, so initial value, that is x is goes on decreases with respect to time, and almost and finally reaches to the 0, that is y axis. Okay, therefore the system is a aperiodic in nature. Okay, therefore the equation 7 and 8 are called as a general solution of the critical damp particular system. So this is about what, while solving the problem, equation number 7 also you can take in terms of velocity, and this is also equation number 8 is also, both are the general solution for the critical damp system. Okay, so up to now we have to write in the examination. Okay, I hope you understand that. Just to remember for the this critical damp system, nothing but critical damp system is nothing but is equal to what? So critically, if the zeta value is equal to 1, then such systems are called as critical damp system. Okay, otherwise c is equal to cc. Okay, so damping is equal to critical damping is called as critical damp system. So again you write the procedure. Okay, in the critical damp system, the roots are real and equal for, and zeta value is equal to 1. Okay, so we know that here the s1 and s2, this is normal equation already we derived while solving the overdamped particular system. Okay, just to substitute, you are going to get s1 and s2. Okay, so because of the repeated roots, so the approximate solution for almost all the systems, we are going to get what? X is equal to 7 e to the power of s1 into t. So just to substitute roots, you are going to get one equation, that is the equation number 1. Okay, so now if you need to calculate the C1 and C2 value, where C1 and C2 are constant value. Okay, just to disturb the whole system, so you are going to get what? Boundary condition. Okay, so just to substitute boundary condition in equation number 1, you are going to get what? C1 and C2 value. Again C1 and C2 value substituted in the final, that is the first equation, you are going to get one generalized equation. Okay, then your differentiate equation number, that after putting the boundary condition you differentiate, you are going to get equation number 4. Okay, so substitute after getting this equation number 4, again you just to resimplify equation number 2 and 3. Okay, so you are going to get what? C1 and C2. Again C1 and C2 value put in the equation number 5, you are going to get the generalized solution of critical damp system. Okay, so this is about the critical damp system. Okay, this is also very important, I will repeat. So here the critical damp system is nothing but what? If the zeta value is equal to 1, overdamped means if the zeta value is greater than 1. Okay, if zeta is less than means underdamped particular system. Okay, all these three systems are very important for the point of examination. I hope you understand this critical damp particular system. Okay, thank you.